Every cell in your body has an intrinsic resting membrane potential, and fluctuations in that potential can be used to signal such things as action potentials or hormone release, or even in some cases, programmed cell death. I'm Tyler Farah, and in this lesson, we're going to take a look at the fundamental physics of electrostatics. Specifically, we're going to talk about how charges that are separated interact. We're going to see what both positive and negative electric potential energies mean in the real world, and we're going to talk about how to calculate work that's done when we move charges closer together or spread them further apart. This lesson asks us to address many topics that a lot of students find challenging, and not just in electrostatics. We've got unit conversions and scientific notation calculations and positive and negative energies and work and this thing about infinity. Let's start there, in fact, with work and infinity. A question for you: what is work? The most common answer to that question is that work is force times distance. And that's definitely a very common way to compute work, but that's not a very fulfilling description of what work is. Work is a transfer of energy. For example, what happens to the energy of the two positively charged particles as I push them closer together? Positive particles repel, so they want to fly apart, and that represents potential energy. Here's the cool thing about work, though. For me to push those particles together, I have to spend energy. And the energy I spend is exactly equal to the energy the particles gain. That's what I mean by a transfer of energy. I lose energy by doing work, but the particles gain energy by having work done on them. So another way to compute work is to compute the amount of energy the particles gain or lose as we push them closer. It's the same for the negative particle. But in this case, pushing it closer is going to mean the particles lose energy, and that's because that third negatively charged particle is attracted to both the first positively charged particle and the second positively charged particle. And finally, in this question, it's going to be important that we have this other way of computing work as the change in energy, since our first plan to use work equals force times distance won't work, pun intended. In fact, why not? Why can't we compute the work in this example using work equals force times distance? The answer is that the particles are initially separated by a distance of infinity, and we can't very well plug infinity into the work equals force times distance equation. So I want to turn your attention next to this notion of infinity, because physicists throw this word around a lot, and it is an idea that's tested on the MCAT too. Believe it or not, saying that two charges are initially separated by a distance of infinity is actually meant to be a simplification. If two particles were separated by a distance of infinity, then their energy of interaction would be zero. Why? The answer comes from the equation for electrostatic potential energy. Here, K is a constant and will be given to you on test day if you need it. Big Q and little q each represent our two charges, and R is the distance between them. Notice that as R gets bigger in magnitude, potential energy gets smaller in magnitude. So as distance approaches infinity, energy approaches zero. Let's put 2 and 2 together. In our question stem, overall, we're asked to find the work done by pushing particles closer together. And a moment ago, we said that one way to calculate work is to calculate the change in energy. Well, now we know that the initial energy of these particles is zero. So if we want to find the change in energy in their final state, how can we do that? Since the particles' initial energy is zero, their final energy is also the change or transfer of energy, aka the work. It's like if you have $0 initially and then I give you $10, then your final balance is $10. And the amount of money you gained is $10. And the amount of money I lost is $10. They're all different ways of saying the same thing. Here, the particle's initial energy is zero. So their final energy also equals the transfer of energy, which also equals the work. Different ways of saying the same thing. This is why the initial infinite separation is a simplification. Now, if we want to know the work done, well, we can see that it's equivalent to just calculating the final energy, and we've already got the equation to do that. But still, I find that a lot of students get tripped up trying to visualize what quote unquote infinity looks like. And so this doesn't seem like a simplification to those students. This first prompt is designed to help you visualize infinity. When a physicist says that two particles are infinitely far apart, what she means is that the particles are far enough apart in the real world that their energy rounds down to zero. For example, in this question, the final energies are going to be in the range of dozens of joules. So we can start with the particles far enough apart so that their energy is equal to 1 millijoule. Well, that's what quote unquote infinity looks like in this context. I want you to see what this looks like in the real world, so I want you to try this calculation for yourself. What distance of separation will get particles 1 and 2 to have an energy of 1 millijoule? This is going to end up being an opportunity for me to teach you a cool hack for doing scientific notation, but first, try the computation yourself. All right, you probably got this far without any serious trouble, but it's at this point where some students start to run into difficulty. If you breezed through this computation, then congratulations. That's actually a skill you should be proud of. But if you didn't, let me help you simplify. First, unit conversions are super important on the MCAT. I guarantee you'll have to do some on every science section of the test. And it's no coincidence that this question uses milli and micro, as these are by far the two most common unit conversions. Remember that for test day, milli represents 10 to the minus third and micro represents 10 to the minus sixth. Still, having done these unit conversions, this looks pretty ugly. So here's the scientific notation hack. When you have a fraction like this, you can separate out the exponents and the mantisses. Those are the numbers out front. Just keep the shape of the fraction the same, the numbers on top stay on top and so on, and you're set. In fact, on many multiple choice MCAT questions, you might only need to compute the mantissa term or the exponent term. This is such an important strategy that I want to check. When on test day would you only need to compute the mantissa, for example? If a multiple choice question has 4 answers with 4 different mantissas, then you really only need to compute the mantissa term. You can just ignore the power of 10. Similarly, if the question has 4 different exponent terms, you really only need to calculate the exponent. But in all cases, I think we can agree that this computation, having been separated out, looks significantly less intimidating. Carrying the calculation through, and remember, for powers of 10, you add exponents in the numerator and subtract exponents that are in the denominator. We get 18 meters. Remember that our goal here is to visualize quote-unquote infinity. And in this question, infinity doesn't mean that the particles are at like opposite ends of the universe. Infinity in this question means that if one particle is in the room with you, the other particle is like out in the hallway. And bringing these particles to their final state means that we're just going to bring that particle from out in the hallway into the room with you and the other particle. That's what infinity looks like in the real world. All right, let's get our hands dirty. First, we're asked why the work done on charges 1 and 2 is positive. And we know that work in this question is equal to the final energy. So this is the same as asking why the final energy of these particles is positive. So let me turn that to you. Why is the work done, aka the final energy of the particles, why is it going to be positive? There are a lot of potential answers to this question, and they're all helpful. First off, we said earlier that 2 positive charges will repel. So we push these positive charges closer together, and they'll want to accelerate away from each other. That's represented as a positive potential energy. Second, if work is a transfer of energy, well, then these particles are gaining energy. So the work done on the particles is positive. It's again like your bank account. Your bank account moves in the positive direction when you gain money. And finally, we represent this idea mathematically because plugging 2 positive charges into the equation gives a positive output. Here's a question for you. Other than 2 positive charges, how else could we get a positive output from this equation? we could use two negative charges. A minus times a minus is also a plus. And the important thing is that physicists have come up with this really elegant equation that works for any pair of like charges. Either way, there's an inverse relationship between distance and energy. When you push two charges closer together, plus plus or minus minus, in both cases, their energy goes up. This should fit with your intuition exactly. That said, we've got to actually calculate the work. We know that the initial energy is essentially zero, so the work is just going to be equal to the final energy. Go ahead and compute the final energy right now. Try out that scientific notation hack for yourself. A sneaky trick by the lesson designers here, the numbers for this computation were actually exactly the same as for the last computation. So the output here is, again, plus 18 joules. These particles are repelling, and that is reflected by their positive final energy and by their gain of energy due to the work done on them. All right, the next prompt question asks about the third charge, and now the negative work done. As always, work is the difference from initial to final energy, and the initial energy is zero, so work is still equal to the final energy. My question for you, mathematically, how would we get negative numbers out of the energy formula? So now, a positive and a negative, or a negative and a positive, will make the energy negative. This is a really challenging concept, negative energies. So I want to spend some time on it. First off, let's start with intuition. Forget the math for a moment. If we bring a negative particle and a positive particle closer together, what happens to their energy? Their energy goes down. You see this with electrons orbiting a nucleus, for example. The core electrons that are closer to the nucleus have a lower energy. The valence electrons, which are furthest from the nucleus, have a higher energy. What that means is that for opposite charges, there's a direct relationship between distance and energy. Reduce distance between opposite charges, reduce energy. This next question is a hard one. How does this same energy equation, U equals KQQ over R, how does this equation show this direct relationship between energy and distance? The answer is the minus sign. We're now in the bottom quadrant of our graph. And notice that in a real sense, as we move down the distance axis, we also literally move down the energy axis. That is, the numbers increase in magnitude, but they're also negative. So they're getting further from zero, which means the energy is going down. This is what minus signs do. They flip relationships. What was an inverse relationship just a moment ago becomes a direct relationship. Here's an analogy. Which is colder, 25 degrees or 3 degrees? It's obviously 3 degrees. But how about minus 25 or minus 3 degrees? Now it's minus 25 that's colder. Minus signs flip relationships. And this is what makes the potential energy equation so mathematically beautiful. If you have like charges, plus plus or minus minus, then you're in the top quadrant. And just like you'd expect, pushing charges together increases their energy. But if you have opposite charges, minus plus or plus minus, then you're in the bottom quadrant. And suddenly, just as you'd expect, pushing these opposite charges together decreases their energy. So remember this now and through test day. Negative energies are just a sign convention. They're just physicists' way of letting you know that you're working with opposite charges. That said, you've got some computations to do. Remember that the third particle is going to interact with both charge 1 and charge 2. So you'll need to compute the energy of each interaction. You can do these computations separately and we'll add them up at the end. So for now, what is the final energy of interaction between particles 1 and 3? And what about between particles 2 and 3? You might have recognized that the exponential terms were the same in this computation as in the last one. In the last computation, the exponents all canceled out, and so I'm not even going to bother writing them in this time. It's all about the mantisses. Another math shortcut here is that charge 2 was actually twice as large as charge 1, but charge 2 is also twice as far away. So those factors just cancel out. Furthermore, there have been a lot of math shortcuts baked into this lesson by the lesson writers. That's not a coincidence. In fact, the test makers also bake math shortcuts into many MCAT questions. Not all MCAT questions, but many of them. And it's like the famous Wayne Gretzky quote, you miss 100% of the shots you don't take. Well, if you are looking for shortcuts on MCAT math, you'll find some of them. But if you aren't looking for shortcuts, you'll miss all of them. One last step, and this is really as much a summary as it is a final computation. So go ahead and take it away. What is the net work done in arranging these particles? Well, as review, because the particles were in an infinite initial separation, which might be like 20 meters in the real world, their initial energy is 0. So calculating work in this question meant just calculating final energy. The positive particles repel, so their energy increased to 18 joules. And as for charge 3, the negative one, it's attracted to charge 1 for minus 27 joules. And it's attracted to charge 2 for another minus 27 joules. All told, the final energy is minus 36 joules. And that means that the work done arranging these was minus 36 as well. This prompt highlights one final advantage of work and energy. We can calculate work for different events individually, or we can calculate energies for different interactions individually, and then just add them up to get the final result. That's a very nice feature. So one last question for you. The fact that the final energy was negative, what does that tell us about the final stability of these particles? The negative final energy tells us that these particles are more stable in their final position than they were initially. Even though charges 1 and 2 repel, they're stabilized by charge 3. If there's one major takeaway from this lesson, it's that work and energy are extremely flexible mathematical tools. They might be a little challenging conceptually at first, but it's worth it to stick with it because these ideas are going to show up everywhere from action potentials to pacemakers and defibrillators.